The main purpose of today's class is to describe the Wehrbein-Einbein formalism of general relativity. At the end of the class, this should hopefully be short, and at the end of the class we will, if we have time, Pranay reminded me we never discussed the Eikenall approximation. We'll do that. In fact, it's particularly relevant since we just discussed gravity waves. Eikenall approximation works also for that. Okay. So, okay, now, you know, the beginning discussion in our course, or a lot of the discussions in the beginning of any book on general relativity, is about this equivalence principle. And the equivalence principle tells you that if you've got any local frame of reference, in any local frame of reference, you see, locally you see physics, special relativistically, independently of what's going on outside. Gravity doesn't matter. If your local inertial frame of reference, so you're freely falling with the gravity, blah, blah, blah. Okay. Now, did this underlay our whole construction of general relativity? But very soon we started looking at arbitrary coordinates. These coordinates went all over space-time, and these local observers went, were not playing a very big role in anything we did. Okay, so in today's class we're going to introduce something like a local reference frame, something like the kind of thing Einstein did when studying special relativity for general relativity. Namely, we're going to try to make a grid of local observers. What does this mean? Mathematically, what we're going to do is, given a space-time, so we've got mathematically what we're going to do is to choose a set of vectors E A mu. Maybe we'll, okay, doesn't matter. We'll choose a set of one forms, E A mu, okay? So maybe I'll start with vectors. I choose a set of vectors E A mu. A is equal to 1 to 4, 0, 1, 2, 3. And mu run over the various coordinates of spacetime. Okay? I will choose these vector fields. EAMUs are vector fields. They're functions of x. There are 4 different vector fields. Okay? The 4 different vector fields labeled by A. Okay? And I will choose them to have the following properties. G mu nu, E A mu, E B nu is equal to eta A B. Okay. Eta is, exactly, -1, a diagonal matrix, the -1 in 0, 1 in space. Okay? At the moment, these A and B indices have nothing to do with space-time. There's some auxiliary indices. Eta A B is just some matrix. Okay? This guy was a function of x. This guy was a function of x. This guy is not a function of x. Now let us first interpret this equation. What does this equation mean? What this equation means is that for any one, first let's choose a, let's look at the diagonal part of this.
We're diagonalizing the space-time metric.
It's true. It's true. It's true. But first, let's look at it this way. E a mu. Let's look at any one of them. E1 mu. E1 mu is a vector field which everywhere has norm 1. E2 mu is a vector field which everywhere has norm 1. E3 mu is a vector field that everywhere has norm 1. And E0 mu is a vector field that everywhere has norm -1. So we've chosen 1 time-like and 3 space-like unit normalized vector fields. But that's not all, because this equation has meaning not just for diagonal terms but also for off-diagonal terms. We've chosen them so that they're everywhere orthogonal. So now, given a time-like and 3 space-like vector fields, we've essentially got a grid in which that little region around, in the little region around the point x, we can set up an almost Minkowskian coordinate system. Okay? So what this is doing is to, yes?
So the norm is 1, but the norm of E0 seems to be -1.
Exactly. So we've got 3 space-like and 1 time-like unit normalized. When a time-like norm vector field is normalized, means it has norm -1. Okay? So you should imagine that in space-time, at every point in space-time, we've set up a little grid. I can't draw it because there's a fourth guy, but 4 of these. These guys can rotate around however you want. Okay? I've done it in an arbitrary way so that these EAs are always obey this condition. Now, something that we'll come back to in a little bit, but we should immediately note, is that it may not always be possible to do this. Okay, can anyone give me an example of a space?
Null submanifolds.
Null submanifolds, that's very complicated. Okay, but just a spatial space, forgetting space-time. A spatial space, a sphere. There's this famous theorem that you cannot find a smooth vector field on a sphere that is everywhere non-zero. Okay? Here, in this, what we need is 4 smooth vector fields that are everywhere non-zero. However, so it may not always be possible to do this globally. However, if the topology of space-time, is that of the inside of a ball, then it's always possible to do it. So at least patch-wise in our space, it will always be possible to do this. Okay? And how to glue different patches together, we'll discuss. Okay? So this may or may not be possible always to do all over our space-time, but it's certainly possible to do patch by patch. And we'll discuss what happens when it's not possible. Okay, good. So the first step in what we're discussing today is this set of vector fields that we have. Vector fields are little elements in the tangent space. You should imagine little arrows everywhere in space. There's this grid of 4 arrows everywhere in space. Now, suppose I've got, let's say, a one-form field A mu. Okay? Suppose I've got a one-form field A mu. Then all of the information that is contained in A mu is equally well contained in AA, which by definition is E mu A A mu. So this is a definition. What does it mean? AA is simply the projection of my vector field, of my one-form field, okay, onto the 8th coordinate axis. The overlap of my vector field with the 8th coordinate axis. Suppose I know AA, I can completely reconstruct the vector field or the one-form field. We'll give explicit formulas in a minute for how to do that. That's clear? So the idea, and what I've said about a vector field applies, let's say, to a 2 tensor or a 3 tensor. I can dot 3 times Okay. So the idea is that there are, once if I give you a choice of this E aim x mu, there are two independent but equivalent ways of specifying any geometrical object. A, by specifying the object itself in some coordinate system. B, by specifying its projections onto your basis of fields. Is this clear? Okay. Now, the question we're going to ask is, suppose I am interested, okay, suppose I am interested in writing my equations of motion, or writing geometrical equations, not in terms of A mu, but in terms of these projection vectors. How can I, is it possible? How can I proceed? Okay, there are two main motivations, there are three main motivations for what we're doing here. The first motivation is the one that, that you asked about last time, which is, how do you formulate Dirac's equation in general relativity? We'll try by the end of this lecture to formulate it. Okay, the second motivation is to understand in what sense general relativity is a gauge theory. And we're going to understand both of these as we go along in today's lecture. Okay, but before we do that, let us first get a few sort of mundane algebraic things out of the way. The first thing I want, there are various things that I want to claim. Okay, firstly I'll define E A mu to be the inverse matrix of E A mu. Okay, so this is defined how? This is defined 2 E mu B is equal to delta AB. And equivalently, because of the properties of inverses, E mu A, E A mu is equal to delta mu.
This requires that this matrix be invertible.
This requires that the matrix be invertible. It's true. It's true. If there is, you see, where might it be non-invertible? It might be non-invertible at places where the coordinate system goes bad. Because you see, physically, our grid is fine because it's unit norm and so on. If the coordinate system goes bad, we may have trouble. Okay, let's leave those special cases aside for now. Okay, we've got a good coordinate system. This will always be possible. Okay, now with these definitions in place, I want to claim various identities. First thing I want to claim, I mean, these are all obvious. I mean, these are all the things you would guess were true, but let's claim them and see if we can prove them. First thing, E A mu, E A nu, sum eta AB. Okay, if we do the sum over A and B, I'm claiming that this quantity is eta AB. Okay, now why is this true? Let's see.
You multiply this by 2 of E.
Exactly. So let's see. So what do I want to do? Substitute what? Yes. Let's see. So this was our definition here. Now, let us check whether if we substitute this in this would be true. Okay. Okay. So let's first do that. Okay. So okay. We have E mu C E D nu eta CD times E A mu E B nu. Is this equal to eta AB? But it's obvious that it is, okay? Because this contracted with this is eta, this contracted with this is delta, sorry, delta AC. This contracted with this is delta BD. And then this becomes eta AB. Okay? So this is equal to eta AB. So at least this check works out. More seriously, how do we prove this more seriously? Let's see. Okay, this would be true. Okay, so I'm sorry. Give me a minute. That's some simple logical manipulation. Sorry. What does one do? Just.
Yeah, we can just multiply and then sum this definition equation. Multiply both the sides by let's say E xi mu and E eta mu, and then sum over mu and mu. We have it.
Sorry, but give us both your suggestions. One of you first. Go.
Okay, so that equation of the definition, yeah.
Yes.
On both sides we multiply E.
This is a good way.
E xi mu and E eta mu.
Okay, let me multiply. E.
Xi mu E eta mu.
Mm,
No, not A. Okay, sure. E A, that works.
E A alpha.
E B beta.
E B beta.
Sum over A.
E A alpha E B beta. This is E. Now we sum over. Perfect. Perfect. This gives it us. Very nice. Thank you. Okay, that's a very nice proof. Okay, so from here he Tunir multiplied E with E on both sides. Use the fact that this guy gives a delta, this guy gives a delta, so we just get G mu. Perfect. Beautiful. Nice proof. Thank you. Okay. Similarly we have E mu A, E nu B, B eta AB is equal to G mu nu. Okay, I'm just going to write down all of these identities and I'll leave you guys to exercise your ingenuity. You're better at it than I am, okay? To prove these things. Okay. And we also have E mu. This we already, that was part of the definition. We also have E A mu E B nu G mu nu is equal to eta AB. All the obvious identities. By contracting work, if you fool around for 2-3 minutes, you'll be able to prove all of these things. Okay, so this we will use repeatedly. Okay. Now, the next thing we're going to ask ourselves is the following. You see, I've set up one set of these E's. Suppose you set up another set of these. Okay? Of course, you will get different for instance, AA components compared to me, because you will be projecting onto a different basis of vectors. So I want to understand what is the connection between your AAs and my AAs. In order to know that, I have to know what is the connection between your EAs and my EAs. But if you think about it, we already know it. Because these EAs are a set of vectors that obey this relationship here. So now suppose I wanted to do E prime A mu is equal to lambda AB E B mu. Suppose I want to do this and to have this relation without Tony's additions, okay, this relation continue to hold. What do I need? I need that eta is invariant under multiplication by lambda, and therefore lambda locally is a Lorentz transformation. Okay, so lambda AB of x is a local Lorentz transformation.
How did we define the prime T's?
By that equation. The prime D's had to be another set of vectors that also obeyed the same identities. Okay, our E's obeyed these identities. We want to know how non-unique the set of E's that obey these identities are. Okay, so I do an arbitrary linear transformation first on these and see that for it to continue to obey this identity, this linear transformation can't be arbitrary. It has to be a Lorentz transformation. This is clear?
Local as in that gets obeyed only in one point.
This is an arbitrary function of x. Because this equation is ultra local. It holds x by x. Okay, so that lambda AB, what lambda AB is at one x is unrelated to what it is at another x. Okay, so you see what we have here is exactly what we have when we are studying when we study a gauge theory. We have a redundancy. Why is it a redundancy? It's because, at least in the absence of spinors, we didn't need these local Lorentz frames to describe physics. We just set them up. And then we decided to project, data with respect to these local frames. Okay? But our local frame was defined by some property. And given one local frame, I can find another which has all the same properties, provided that the transformation between the two frames is given by this equation. Okay? So anything that you can say with your AAs, I will be able to say with my AAs. Okay, provided my A's are related to your, my E's, these Wehrbein fields are related to your E's by these local Lorentz transformations. It's important as local. Yes.
So this transformation can be done by coordinate transformation also.
Well, at the moment, we're not doing a coordinate transformation. The coordinate transformation affects the mu index. That is not being touched. What we're doing is changing these A's. You see, it's important that what we're doing is not a coordinate transformation. You should think of the choice of E's as literal geometrical vector fields on our manifold. Two people using different coordinates can describe the same choice of E's. Okay? It's like, suppose we've got a two-dimensional space. I actually draw in my two-dimensional space a choice of things. I've drawn it on that sheet of paper. Then you can describe that in any coordinates you want. These actual physical choices. There is one vector field, it's geometrical objects unrelated to the coordinates. There's another vector field, it's another geometrical object unrelated to the coordinates. And there's ambiguity in the choice of these geometrical objects.
So you're transforming the vectors.
I'm changing the vector fields. This was a choice of a 4-parameter set of vector fields, and I can change this set of 4-parameter set of vector fields by such a transformation.
In the same coordinates.
Yeah, the coordinates actually matter not at all because it's a covariant equation. Yes, I'm doing it in the same coordinates. But you could, the same coordinates, but it could be any coordinates. Is this clear? I've got an actual physical geometrical vector field, and I'm making linear combinations of those geometrical vector fields to give you another vector field. Is this clear? Okay? Yes?
And this freedom is not the coordinate choosing freedom. I mean,
Unrelated.
okay.
Unrelated.
Extra freedom with the system, we can choose the basis.
Completely independent of coordinates. Coordinates are one thing, these basis vectors are another. If you want to describe these basis vectors, you'll have to describe them in some coordinates. But they're geometrical objects, they're things. They're things out there.
How do these E, mu, B obey this equation?
How do they obey the equation? What was the equation? It was G mu nu E mu A E mu B was equal to eta AB. Now we'll put this in. Okay, so what do we get? We get, so let me check if this guy obeys it or not. Okay, or even simpler, what I'll do is put this in terms of that. Okay, so I know this and I'll substitute that. So I get G mu nu E mu A E nu A prime E nu B prime, and then lambda A prime lambda B prime. That's the thing I want. But this guy by definition was A prime eta A prime B prime. So my transform thing is this, but this I know is this times.
Isn't that the inverse of lambda, not lambda?
Well, I'll change my lambda if you want. It doesn't matter at all. Right? Lambda B prime B. I may have done it the other way. It doesn't matter, right? I change one to the other. But that is equal to A eta AB, but that's the thing that defines Lorentz transformations. A Lorentz transformation is that transformation that leaves eta invariant.
Right. So we impose that this needs to be true, and that gives the.
I impose that both before and after the change of these vector fields, the same equation is true. Okay? Here I used that, let's say, before it was true. This is the claim that it's true also after. Okay, so we get this equation.
Yes, and this equation gets followed all over the manifold.
Everywhere.
Then why is it a local Lorentz transform?
Because this guy could be a function of x. It could be a separate choice of Lorentz transformation at every x. This equation has no x on the right hand side. But you could choose a boost here with a parameter that changes. Yes?
Why should there be linear transformation between them?
Why should there be linear transformations between them? Okay. There may also be more complicated transformations, but you know, there may be more complicated transformations in special cases, using special properties of these E's. Okay. If there is okay, let me just say this. If there is a bigger redundancy, that will have its own implications. I'm looking at least the implications of this redundancy. Okay. You know, these vector fields are things that we think of in tangent space. Okay? And it's very natural to add and subtract them. So linearity is a very nice thing to maintain. when we're looking at vector fields. That's the geometrical intuition. But perhaps there's something more you can do, in which case you might discover more. Okay, but at least this is a redundancy of what we're doing. Okay, great. Now, the next question I'm going to ask is the following. Suppose I have, I'm interested in taking some derivative of AA.
Last part. What is this local, as in how is it this local transformation different from a regular Lorentz transformation?
A regular Lorentz transformation firstly only applies in flat space and is labeled by one matrix, just one 4x4 matrix that has some properties. This applies in an arbitrary curve manifold and is labeled by a function of such 4x4 matrices.
Function of 4x4 matrices is a function of a 4x4 matrix is a function of the point.
A 4x4, sorry, you're right. A function of 4x4 matrix, which is a function of the 4-dimensional manifold.
But a Lorentz transformation is anyway defined only on one tangent space.
In special relativity, a Lorentz transformation is defined all over the space.
Yes.
That's what I'm used to calling a Lorentz transformation. This is a local version of that.
Yeah. So on a curved manifold, this is the only kind of Lorentz transformation that can be.
This is the only kind of a Lorentz transformation that can be. I'm just saying that when you compare with special relativity, where you had an invariance with one matrix, this is much more. Okay? This is very similar to what we do in going to study electromagnetism. We notice that a theory has invariance under a phasing of the, let's say, psi field. And then we ask what happens to the theory when we do local phasing of the psi field. That leads us to the structure of electromagnetism. Okay? That's a much larger thing to do than the global phasing that you started out with. It's very similar. The analogy is somewhat like that. Okay, you go from a number to a function. From a matrix to a matrix valued function. Okay. Okay. So now suppose I was interested in computing derivatives of AA. Okay. Suppose I was interested in computing some derivative of AA. Okay. Now let's remember what this is. AA was this is the derivative of del mu of EA mu. Okay, this is a derivative del mu of EA mu. A mu. If I just took an ordinary derivative of this object doesn't obviously have any space-time indices. Okay, so you might think it's a space-time scalar. However, though it's a space-time scalar, it has some ambiguity in it. It depends on your choice of Vierbein fields. This tetrad, sometimes called Einbein, Vierbein, all kinds of German things go in here. Okay, so some sort of whatever, this thing. Okay, it depends on your choice of this thing. Okay, so let's see how it depends on your choice of this thing.
So do you use other than mu is the derivative index?
What?
Mu is the derivative index.
Thank you. No more talks. Okay. Thank you. Okay. Let's see how this thing depends on our choice of fields. Okay. So suppose we take this del alpha, which is none of these, the space-time index is not affected by choice, and we do a lambda a b e b mu a mu. This is the function of x. So I do the variable change, so this goes to this with a tilde if you want. Okay? Now, what do I get? There is one term which is just lambda AB times del alpha E tilde B mu A mu. But this E tilde mu B mu is A. So this term, which is equal to lambda AB A, let's call it tilde B. A reflected, projected onto the tilde axis. However, del alpha, yes. However, there is a second term. That second term acts on this this object here. So that term is plus del alpha lambda AB times A tilde B. So we see that the naive derivative of AA, okay, is of course not independent of the choice of Vierbein fields. Now we're going to use the fact that we're all experienced gauge theorists to try to fix this up. You know, in gauge theory we run into the same problem, and you study electromagnetism, you ran into the same problem. And let's remember what you did, except that this is a non-abelian. This is a non-abelian case, but anyway, what you did was, what we're going to do is to say, well, suppose I define an omega mu AB, which is the gauge field. Okay, this is called the spin connection. But it's the gauge field that will compensate for this local Lorentz change. It's a connection that allows you to compare. You know, geometrically, why is all this happening? It's because we're trying to subtract a vector field projected onto the basis here with a vector field projected onto the basis there. But we can't do that unless we know how to compare the basis vectors here and there. In order to be able to do that, we need a connection. So we need a connection to be able to compare the basis vectors.
So how does this differ from the usual Christoffel connection?
Coming. It will be related, but it's not the same because it's got different indices. But it will be closely related. Okay? So we define this with the property that we demand that under this change from untilde to tilde, omega mu nu AB, okay, omega mu nu AB goes to omega tilde mu AB okay. So in order to figure this out, let's first write down what we're going to do is to change d alpha going to d alpha plus omega alpha AB. This is the definition. Then we will find how to compute it using certain properties that we will require of it. Okay? But this is the definition. It's a connection that we add to the derivative. Okay? And we are going to require that under this, under a local Lorentz transformation, this derivative transform homogeneously. That is going to be our requirement. A what?
I mean, the derivative has a linear piscum. Delta alpha A B.
Yeah. Delta AB. That's what you were saying? Yes, thank you. Okay, so let's call this d alpha. D alpha is equal to this. And we'll try to determine the transformation property of omega under a local Lorentz transformation so that this derivative operator transforms homogeneously. Okay, this will be our goal. Okay, so let's get down to doing it. So what?
Should be consistent. The left hand side should also be d alpha delta AB.
Left.
The left hand.
Left hand here?
Yeah, I mean, shouldn't there be AB in this?
Yeah. D alpha AB. Okay, so we want to define d alpha as you say AB acting on psi B, and that is defined by this del alpha psi B, psi A plus omega alpha AB psi B. This is our definition of this covariant derivative in terms of this as yet unspecified object.
Size are four scalar fields, right?
Size are what we call A's, sorry. There are 4 scalar fields under coordinates, but they transform like sort of vectors under the change of this. Now we're going to define this with the requirement. What we want of this definition, okay, is that under E A mu goes to omega A B E B mu, lambda equals lambda A B mu, we want D A to go to lambda A B D B D A B. That is the thing we want. Okay? And we have to determine how omega transforms, how omega must transform under this local Lorentz transformation to make sure that this is true. Okay? Okay, so let's see. So, firstly, let us write down what the original thing was. It was this. And then we will transform AA. So this is d alpha of, so this goes to what? It goes to lambda AB plus omega alpha AB B prime lambda B prime C prime A C prime. Okay, so one term is what we want because we take the del alpha out here. So it's lambda A B times del alpha A B. That's as we wanted. Okay, but what are the remaining terms? Okay, there's plus del alpha lambda AB, lambda AB plus omega alpha A. Okay, now I'll write this in matrix notation just to simplify. Omega lambda A. Okay, I'll write this also in matrix notation just to simplify. So it's del lambda A. So this is a matrix equation. But I want this whole thing to be lambda times the new omega times A, del alpha, omega alpha. This whole thing has to be this. Okay? And so let's write that equation out again. It's that del alpha lambda plus omega alpha lambda has to be equal to lambda omega alpha. It's acting on an arbitrary column on both sides, but the column is totally arbitrary, so this must be true of the matrices. And this is prime, the new guy. And therefore omega alpha prime must be equal to lambda inverse del alpha lambda plus lambda inverse omega alpha lambda. Okay?
Shouldn't that be just omega alpha plus?
Oh, it looks good to me.
No, I mean the second term.
This one?
Yeah, because and here you just chose to write it as lambda omega alpha A, but if you were to be consistent with this, that should have been omega lambda A. This term. I mean, the last term remains as it is, but what you wanted to do was write it as omega prime lambda A, wasn't it?
No, I wanted it to be lambda times omega prime A. Right? You see, what I wanted was a Lorentz transformation of the new covariant derivative.
I see.
Okay? We could equally well rewrite this in terms of, I've got omega prime in terms of omega, I can get omega in terms of omega prime.
Yeah, in case of abelian gauge theory, that would be simply omega.
That's right. That's right. That's right. But this is not abelian. Yes.
That's what I was confused.
Yes. Okay. If you want, we can rewrite this in terms of, we could rewrite the whole thing to get omega in terms of omega prime. Let's do that. What we have is that lambda inverse omega alpha lambda is equal to omega alpha prime minus lambda inverse del alpha lambda. And now I multiply both sides by, I multiply by lambda here, lambda inverse here. So I get omega alpha is equal to lambda omega alpha prime lambda prime. Okay. Now the lambda inverse cancels, and I get del alpha lambda and lambda inverse. Well, this is also true. They're equivalent relations. Okay? So if we did the change that we did, accompanied by this change of spin connection. Okay? The change that we did accompanied by this change of spin connection. Okay? So let's write it out finally. What is our final conclusion? Suppose we have, I'll try to be clear. Suppose we have d alpha is equal to del alpha plus omega alpha A, just in matrix notation. Okay? And we define A is equal to lambda A prime we also define omega alpha. Alpha is equal to lambda omega alpha prime lambda inverse. Sorry, this is lambda inverse minus del alpha lambda inverse. We do these two things, then d alpha a is equal to lambda times d alpha a prime, where d alpha a prime is now defined with the primed spin connection.
This E alpha should not be there. D alpha is equal to del alpha plus omega.
You're right. D alpha, yeah. Sorry. D alpha, yeah, it's a AA. Okay, this is the final claim. Is this clear? So, suppose someone were to give you any questions about this?
One question about indices. So omega alpha has two indices, right?
Omega alpha is either 1 or 3 depending how you count. It's omega alpha, one spacetime index and two Weerbein indices. It's a matrix. Right? Omega, when we first wrote it, was like this. And now I'm not writing the AB indices because we've gone to matrix notation. So this is a column. So if you want, I just don't do this.
D alpha prime A prime.
D alpha prime, you're right. Thank you. So D alpha. Okay, I'm just not I'm nowhere am I writing the AB indices now because we switched to matrix notation for the AB indices. Just to keep all formulas manageable. So we make them more transparent. Is this clear? Okay. So now suppose someone were to supply you with a spin connection with these properties, then you have a nice way of differentiating these component fields. But you know, we really don't want to start multiplying the structures in general relativity. If in addition to the metric, I have to ask somebody to supply me with the spin connection and so on, this sort of sounds like it's getting out of hand. Okay? So what I'm going to do is two things. First, I'm going to take a pragmatic approach and give you write down an equation that will help us to determine the spin connection in terms of metric data. Okay? And then at the end of this, I will show you an action principle in which the spin connection fields are an independent degree of freedom, and the equation of motion that I give you will turn out to be the equation of motion, the relation that I give you will turn out to be the equation of motion for these independent degrees of freedom. But that, you'll see how that works. Okay, you'll see how that works. But for now, let us first take the pragmatic approach just to see where we are heading.
One question. For this thing to work, the scalar fields has to come in sets of 4, right?
What?
The scalar field A has to come in sets of 4. It can't be just one scalar field.
Yeah. A is the projection of a whole vector field onto all 4 Weerbein fields. You remember what we started with? We started with these 4 sets of Weerbein fields. We've got a genuine vector field and we project onto each of the components. So AA was a proxy for a vector field. So it does come into sets of 4. Okay? Now, I've told you how to define how to define a covariant derivative for an object with one lower index, but it's totally clear how to generalize this to n lower indices, or to n lower indices and m upper indices. Right? It's just that that each index transforms in its own way, and so for each index we will need a spin connection.
So omega mu upper and omega mu lower, they would in general, how would they be connected? I mean, just by metric.
Yeah.
Lower, right?
Omega alpha is just in space-time is an ordinary one-form field. Okay. I'll come back with some examples for how that works, but at the moment we don't even need that. Now, so far we've talked about what the covariant derivative is for an object with these Wehrbein indices, with no space-time indices. Earlier in this course, we carefully defined covariant derivatives for the objects with space-time indices, but no Wehrbein indices. If we ever have occasion to deal with an object that has both space-time indices and Wehrbein indices, I'll define this to include both the spin connection for every occurrence of the Wehrbein index and the Christoffel symbol for every occurrence of the space-time index. Okay?
Then this del may have the index of A, or
then this del, it's just, so for instance, no, this del is just, it acts with, it's a matrix in the AB space, just like this was here.
yeah.
It's a matrix in the full AB space like this was. Yeah, but that's the derivative part is diagonal in that matrix, and the spin connection part is not. But it acts index by index, as always the case. Okay? Yes?
So something like this, you're taking a tensor,
Yes.
and you're projecting parts, some components of the tensor onto a basis, and then you're looking at how the entire object varies. You're not projecting all of them out.
You, for instance, suppose I had a 2-index tensor, I could imagine projecting one index of it.
Why would you ever do that?
Why would you? Let's look at an example. Let us look now at an object that is mixed. Can anyone name an object that's mixed that we've encountered in this class? EA mu. Okay, that is a natural object that is mixed. Okay, EA mu. We are going to impose the condition that this object is equal to 0. What?
To be consistent, when you write A mu, you should also be putting back the AB indices in the covariant derivative. Right?
Yeah, I should. Still, I'll remove that. Just remember secretly that it has this. I'll use matrix notation always for.
This assumption is, this implies that del covariant derivative of G mu is 0.
Yes, it will imply that the covariant derivative of G mu nu is equal to 0, simply because G mu nu del alpha is G mu nu is equal to del alpha of E mu A E B nu eta AB. And then each of these is 0, so that is 0. Okay, you can convince yourself that if this is true, the same must be true of its inverse. It's obvious, because you use the equation that this tens inverse is equal to. Can everyone see that? Should I do it? Okay, I mean, let me just, it's clear, right? So let's take del alpha of E. You won't scold me if I write indices, just to make it clearer. Okay. Okay. So suppose I write, for instance, E mu A E A nu. Suppose I take this object, for instance. Okay, and I write that it's 0. So it's a product of two covariant derivatives, because covariant derivatives always act by Leibniz rule. One of them is 0, so the other one is also, so some matrix times the other one is 0, but that matrix is an invertible matrix. and therefore the other one is 0. Right? Okay, so if this is true, it's also true for the inverse. So every object E with either mu upper and A lower, or A upper and mu lower, is every object has covariant derivative 0. Okay, therefore, as we've just shown, this guy is 0. Okay, so this is nice. This is nice, but we should think of this as an equation.
Just a tangential question.
Yeah.
So there would be some when we have both, let's say, for want of a better word, both covariant and contravariant EAB.
Yes.
Let's see, A upper and A lower. Then there should be analogs of omega with both this Vauban indices raised or Vauban indices lowered.
Yes. Let me get back to that in 5 minutes. Exactly. It's the way we usually work in a gauge theory. You know, one way of thinking is to dot the abstract vector field with the generator. Okay, so we know what the generator is of Lorentz transformations is on lower indices. You just replace that with the generator on upper indices. Hang on for 2 minutes. We'll come to that in more detail. Okay, you understand, right? Just the way the same gauge field allows you to compute covariant derivatives in many different representations. In the same way, we will work this out here. Okay, but and that will essentially be just some raising lowering. In this case, it will be just effectively raising and lowering. Okay, in this case, it will just be raising one index and lowering an index. But I'll describe that in detail in a little bit. Fine. Let me look at this equation here. Okay, this equation, how many indices does it have? This guy has an A index. So how many indices does it have? This object has
4 indices in total. No, 3.
3 indices.
Yeah.
Right? Because there was mu, A, and alpha. Okay? So this object looks like it has at least, let me do some naive counting. Let me do some.
When the covariant derivative acts on G mu, the indices don't have to be contracted, but when you wrote del alpha E mu A, like it looks like you're contracting the tetrad indices of
Here?
in the first case. Yeah.
No. This is alpha mu A.
The tetrad indices, are they contracted for E and del?
Del.
Yeah. The tetrad indices.
Yeah, no, this is just like del. Let me write it out with all indices.
Yeah.
Okay, this object is del alpha E mu A plus gamma mu alpha beta E beta A plus omega mu omega alpha A B E B mu is equal to 0.
So how does del alpha G mu equal to 0 follow from that?
How does del alpha G mu equal to 0 follow from this? Well, these indices all are contracted.
Yeah.
So we just use Lorentz rule. So this del,
That acts on the first one, but it's not contracted with the tetrad indices of tetrad index.
well, it is contracted through an eta AB.
They are all contracted. Can you just write down all the
Right out. Come, let's write it. Okay. Okay. So firstly, del alpha E A mu E B nu eta AB. Okay. is equal to del alpha.
This follows Leibniz rule, right?
It follows Leibniz rule. E mu A times E b nu times eta ab plus. Is this confusing? That's what it means. The Leibniz rule says that you compute this whole object and take its eighth component. Okay. Similarly here, you take its whole object, compare, but this is just 0. Covariant derivatives follow the Leibniz rule in this way.
Okay, sure.
Is this clear? Yeah. And it's sort of interesting that this object here had no AB index in it. This covariant derivative, it's like this interesting thing, right? That, for instance, suppose we had, suppose in a gauge theory you have an adjoint object, like a matrix. You take trace m to the cube, for instance, m to the 4. You take the derivative here. This object is in the singlet representation. But it obeys the Leibniz rule, remembering that m's were an adjoint representation. Okay, the appearance, this object is ordinary derivative with no spin connect, with no gauge field. But appearances of gauge fields cancel out when you use Leibniz rule for each object appropriate to its representation, because the indices contract. Sorry, is this clear? Is anyone else confused about this? Is it clear to everyone? Okay, excellent. Okay, so now the next question we're going to, okay, I'm going to have to go very soon, but okay, the next question that we're going to ask is let's count these equations. Okay, suppose we were in 4 dimensions. Let's count these equations. Naively, there are 4 into 4 into 4 equations. Naively, there's no connection between these equations. Okay?
Just a tiny remark. So if we raise the index of this omega, the Weber indices, omega AB, it would be antisymmetric in AB, right?
Correct.
Yeah.
It will be antisymmetric. Absolutely.
That would.
Exactly right. Exactly right. Exactly right. Exactly right.
One other question.
Yes.
When you write E mu, we're supposed to think of this thing as a tuple of 4 vector fields.
What?
Just E mu and not E a mu.
When I write E mu, the A index is just suppressed. So it's 16 object, 16 component object we're looking at.
And the A coming inside or outside of that bracket?
This outside is important. This means del alpha, I'm not keeping track of the spin correction, the Christoffel symbol part. This means del alpha E mu A plus omega mu E B A B. This is what it means. Act on this with this and take the 8th component. It may actually be proportional to some other component of E, like in covariant derivatives. Right? When we talk about the covariant derivative of A0, you may get a term that actually is proportional to AI. It's just like that. The bth component of after you've taken the covariant derivative. Is this clear?
And one also has to be very careful about the placement of the Weber indices in omega, right? And the same deal with this spinor indices, this dotted and undotted indices.
What do you mean?
No, I mean one has to be very careful with the placement. I mean, the first slot is lower or the second slot is lower. That one has to be careful with, like in dealing with dotted and undotted indices.
Yeah, right. It's true that lower and upper indices are not equivalent because we're dealing with SO3, 1. Had we been actually dealing with SO4, they would have been basically equivalent. So you have to keep track of lower versus upper. And it's true that upper and lower are not Not equivalent. They are equivalent up to a minus sign once you. So you have to be careful about such things. It's very similar. Everything here is very similar to an ordinary non-abelian gauge theory. So if you have any experience in dealing with covariant derivatives for an ordinary, let's say an SUN gauge theory, everything I've said is the same there. The one thing that is different is that you don't have these factors of omega. You don't have these etas floating around. There, in non-abelian gauge theories, those would be replaced by delta AB, because we usually deal with compact groups. So that's one small difference. Otherwise, everything's very similar to now. Okay? Yeah.
On the left side, in the lowermost line, you have del alpha E mu and then an A above. The del alpha is a normal covariant derivative, right?
Yeah, and that should have been an alpha. The del alpha is the normal covariant derivative, which has a Christoffel symbol.
So here, I'm a little confused about this. So the way you wrote down the full expression for del alpha E mu A
Yes.
downstairs, there's an omega ahead.
Yes.
So if you change, if you make a local Lorentz transformation, your omegas will change and hence del alpha will also change. So I don't understand why the del alphas don't have AB indices.
Why the del alphas do have the AB indices.
So they just suppressed.
Yeah, they just suppressed.
Sorry.
Okay, so everywhere we write, yeah, this is what del alpha means.
So you're contracting one of the AB indices and you're looking at the component of that.
I write this whole thing acts on EA is a matrix in AB space. When I write this with A written here, it's a matrix in AB space acting on a column in AB space. So finally you get a column, and I'm writing the 8th component of the answer. I'm sorry for being confusing. Is this clear? Okay, excellent. So now what do we want to do? Okay, yeah, we were looking at this guy here. This guy here has how many components? We said 4 into 4 into 4, so 64. Okay, but I want to understand how many of these components, are giving me new information. You see, part of what this is telling me is this equation. And that is the equation we use to determine the Christoffel symbols. Okay? So, D into the number of components of a symmetric tensor, we've already used. So let's work around general dimensions. Total number of indices was D cube. The total number of equations was D cube. How much did we already know? We knew D into D plus 1 by 2 of these. These were the ones that we used to determine the Christoffel symbols, if you go back to the beginning of the course. What is left? Well, clearly D into the number of components of an antisymmetric tensor. So D into D minus 1 by 2. But Upanyu has just reminded us that once we raise and lower indices appropriately, omega is an effectively antisymmetric tensor. The number of components in a Lorentz in the adjoint of omega is like in the adjoint of SO4. Right? If you ignore the comma 1, it's just like SO4. It's an antisymmetric tensor. So that's exactly the number of components that are left over. So these equations are exactly as many in number as we need to solve for omega. Or another way of saying this is that this full set of equations is enough to solve for both the Christoffel symbols and for the spin connection. You see, the Christoffel symbol had the feature that it was symmetric times vector. The spin connection has the feature that, at least for counting purposes, it's antisymmetric times vector. Put them together, you get arbitrary matrix times vector, which is the number of equations we have. Okay? So this condition here is sufficient to completely determine the spin connection.
But the Christoffel symbol would still remain torsion free.
Exactly. the Christoffel, by this condition, the Christoffel symbol is completely determined so far by this equation. Later on, physics will force us to modify that when we add spinors. Okay, at the moment, yeah.
Previously, we have left some information about, omega or the.
Previously, we left information. Previously, omega was just any connection. Now, by imposing this equation, we determine the connection omega in terms of the metric data and your ease. Okay? So this is very beautiful, because now, if you give me your ease, there's no free play anymore. Your ease plus this equation determines your omegas, determines your spin connections. So if I give you a known manifold, let's say I give you, I've said all this in space-time, but everything that we're doing is geometry at the moment. And we could do it just in Euclidean space, in manifolds of Euclidean signature. Suppose I give you a two-sphere, and in some patch, I can't do it everywhere, but in some patch, I give you a Vierbein field. Let's say d by d theta and appropriately normalized d by d phi. Okay? And I ask you, what is the spin connection field? If you're going to satisfy this equation, there is no ambiguity, you know it. Okay? So given the Vierbein fields, okay, so I give you the Vierbein fields, the fact that they are a Vierbein determines the metric of the space. Suppose I give you two Vierbein fields. The fact that they are Vierbeins, namely that they determines the metric of the space, because then you dot two of them, you get the metric. Okay? So, and then the fact that this thing should be torsion free, that this vanish, determines also the spin connection of our space.
So the Vierbein contains more information than the metric itself.
It contains the metric, contains the spin connection, the Vierbein plus this requirement.
Okay.
Okay? Determines the metric, determines the spin connection, determines everything. There's no free play anymore.
So we can't prove the del alpha E mu A from this del alpha G mu A.
What? No. That's
and then we can go.
exactly. You see how you are actually free in some mathematicians will sometimes look at structures in which the spin connection is not metric compatible. This is called metric compatibility. For their own purposes, they may find it useful to do that. This is a logically independent structure. However, there is a natural equation one can put on it, which allows you to determine a spin connection that is completely determined by geometry. There's no more free play. And that's nice. We don't want new degrees of freedom. We just want a new mathematical description of the old structure with the old degrees of freedom. Okay? So this is the key equation. This equation determines the spin connection.
Is this the only metric compatible spin connection that you can define?
But this is what we mean by metric compatible. Okay? Now, physics will sometimes force us, as we will see, to change this condition.
Yeah, the 64 conditions will determine the 64 Christoffel symbols
and the spin connections. And if you've got some other natural thing to put on the right hand side, as sometimes we will have, then we may on physical grounds require to change this. There's nothing holy or sacrosanct about this. Just a condition at the moment we're imposing. But it's a good condition because it determines a set of spin connection fields that have all the properties we need to allow us to define covariant derivatives.
So can you define metric compatibility exactly?
This condition. This equation is metric compatible. This equation, okay, on the spin connections and the Christoffel symbols, tell us that the Christoffel symbols and spin connections are metric compatible. Please.
Two questions.
Go on.
How is the spin connection antisymmetric?
How is the spin connection antisymmetric? Okay. Okay, so let's see. It's either antisymmetric or antisymmetric with these lambdas. Just a minute, I'll tell you in a minute. But probably not because. Yes. So suppose we look at omega mu AB acting on AB. Now, you see, let's see. How do we think of this? You see, one way of thinking of this is as follows. Consider any object that transforms in any representation of SO3, 1. Okay? What we want is some omega mu which labels infinitesimal directions in SO3, 1. Okay? Dotted with, so let's call those indices abstractly alpha. Oh, let's call those indices A. Okay? Dotted with TA acting in an AB space on B. If this is absolutely any object that transforms under SO3, 1, this is how we're going to define the spin connection. Okay? Now, so the fundamental object here is this object. And then here what we're going to do is to put various different representation matrices. Okay? So, first thing we want to understand is what are these objects? What is this index? So, this index here labels different infinitesimal elements of the Lorentz group. Okay? So, the different infinitesimal elements of the Lorentz group are precisely, actually, so not, okay, antisymmetric up to, yeah, are precisely those, wait, so let's look at that, let's see what those are. Okay, what we want is the condition that lambda eta lambda is equal to eta. Okay, so, yeah, so we want the condition lambda eta lambda is equal to eta. And so, this, now we'll set lambda is equal to 1 plus something small. Okay, so let's call that 1 plus s. So we get s eta plus eta and wait, here did we want to transpose? Transpose. So we get eta s transpose is equal to eta is equal to 0. Is equal to 0. And so we're going to get that S transpose is equal to minus eta inverse the same as eta S eta. Okay, so these are going to infinitesimal elements are going to be labeled by this, and in fact this is the defining representation. So this description here, I didn't need to do this complicated stuff. So these guys, so this omega with one upper lower indices obeys this property.
Why?
The same reason.
Why do omega parameterize this Lorentz matrix? So these are like parameters in a Lorentz matrix, right? This SS.
Yeah. Why do omega parameterize these Lorentz matrices? See, this is the structure. You've got this times this. Now this guy on vector indices is just the, okay, let's. let's see, let me understand. What is the question? Why do omegas, you're asking why are omegas labeled by infinitesimal Lorentz rotations? Because omegas have to cancel d mu, lambda, lambda inverse, which are infinitesimal Lorentz rotations. Do you understand? You go to the frame where this is lambda. So this is an infinitesimal Lorentz rotation. So if you want, you could put more in omega. But that would be unnecessary. Okay? So omegas are built to be able to cancel this object. Okay? And these objects are infinitesimal Lorentz rotations. So omegas are parametrized by infinitesimal Lorentz rotations in any particular representation. Is this clear? Okay, fine. What was the other?
Do I have any geometrical intuition for that? Like for metric compatibility of G mu, we had like it connects the affine connection of the one forms with the vectors.
Yeah.
Do I have anything?
Yeah. This basically, well, basically it's telling the practical consequence, geometrical consequence, is that if I take the covariant derivative of AA, or I take the covariant derivative of A mu, I'll get the same answer. Okay? So there are two things I could have done, right? I could have differentiated A mu using Christoffel symbols, or I could have differentiated AA using my spin connection. A mu has no little a indices, so it didn't care about the spin connection. AA has no space-time indices, so it didn't care about the Christoffel symbol. So these look like completely different things.
Yeah.
But because that is 0, we'll get the same answer. Okay. That is, if I first covariant differentiate A mu, and then I project onto A, okay, I'll get the same thing as projecting and then differentiating. Okay? So that's why it's a useful thing. It's a useful thing which basically because it tells us that even in derivatives, you can as well work with the AA indices as with the A mu indices. You lose absolutely no information if this is the case. Now, if this was not the case, but it was something known, there's still as much information, but it's more irritating. Okay, but here it's very simple. Okay? Great. Great. Any other questions or comments? Okay. Now, okay, we need to stop, but we'll have to finish this. Okay, sorry, firstly, next week, I'm going to be out of town all week. I'm sorry for this, but we won't be able to have the class next week. Okay, and the next class will be week after next. Okay, yeah, so next class will be week after next, sorry about that. Okay, I'm going to have to finish this discussion, we're going to have to complete our discussion on this stuff when we resume about 10-15 days from 10 days or so from now. Let me just leave you with the main points. Okay, what have we found so far? We found the structure with these vector fields, these Einbein fields. We found this natural. We've discovered the connection between these vector fields and the metric and so on. We've learnt about the spin connection. Okay. By the way, notice check. Well, it's the same thing, so it's not with an exercise. But check that del m of eta ab, or del m of eta following del of eta, del mu of eta is equal to 0. You know how to do it, right? You write eta in terms of dot products of two e's, and then you use it.
That's what we use to show that it's metric compatible.
That's what we use to show that it's metric. In fact, maybe this is. That's what we use to show that it's metric compatible. It's true. That's what we use to show that it's metric compatible. So you could start by showing this. No, but then you want to know why is the contraction of the metric. Yeah, both are true. Okay, let me try to. If you use the definition of eta, let me let me see how.
One of these properties has to be post-selected.
No, I don't think anything. Well, I don't think anything needs. Maybe. Let me think. Just a minute. Well, let's see. Let's look at this by definition. Okay. So this by definition will be. I think it's going to come down to this actually. Let's see. One term is just the derivative, but that's 0 because eta is independent of everything. Okay. So what we're going to do is get del omega mu, and now we'll get eta. So let's say this guy was both indices down. Okay. So this will be a prime, a prime. Okay. Plus omega mu, then eta a b prime, b prime b is equal to, what is this object? That's the question. But this quantity here,
Can we in fact use it as a proof of antisymmetry?
the way I think of it, antisymmetry is built into what I mean by my omega. Yeah, and then this is basically antisymmetry, right?
Yeah.
Okay, so this is 0 more fundamentally than the dotting. Okay, and then the metric compatibility works. Okay, great. Okay, great. So where are we? So what have we done so far? We've set up this Vierbein field, we've defined the spin connection, and so on. Now, where are we going to go with this? We're going to go in two places. Firstly, we're going to answer Manju's question about how do we set up, Dirac equation. Let me immediately answer that and we can stop today's lecture. Move on to the next class. Okay. How do we set up Dirac's equation? Let us look at what Dirac's equation was. Dirac's equation in flat space was, or Dirac's Lagrangian in flat space was psi bar d slash psi. Psi bar and psi were spinors. Now, the difficult thing was that spinorial representations are properties of SO groups. They're not properties of, GL groups. And general coordinate transformations were sort of like GL groups. Okay? So, the difficult thing about writing down Dirac's equation was how to generalize this in some generally covariant way. But now that we've got these basis vectors, these basis vectors, there's no real issue. Okay? In this basis vector space, let me choose some gamma A matrices. Let me choose some gamma A matrices associated with my basis vector space. These gamma A matrices will transform under local Lorentz transformations, like their indices imply. Okay? Now that I have these gamma A matrices, I can set up an equation which is d slash of psi. I set up the operator d slash of psi. What is d slash? D slash is del gamma A times del A of psi. And what does del A mean?
Del is a covariant derivative.
Del A is a covariant derivative, covariant with respect to the spin connection. But first I have to define what, it's covariant. It's a dA. Right? Whereby dA, what I mean is gamma A E A mu d mu of psi. What does d mu of psi mean? Okay, what does d mu of psi mean? D mu of psi means what? D mu of psi is d mu plus, and now we use this way of thinking. We have omega mu AB, let's say, times the generator of Lorentz transformations in the spinor representation. Okay, now you guys will help me get this right. There's some i's and there are 4's and so on. So I by 4, you'll forgive me if my factors are wrong. What? Gamma A, gamma B, yes. I might have got a minus sign wrong, I might have got a factor wrong, but you understand. Yeah. Okay, this thing is now guaranteed to be covariant under local Lorentz transformations. The same algebra that ensured the covariant derivative on vectors ensures this. Well, this is the basic data. It's the same omega AB. It just happened to act faithfully in the vector representation. But now we dot it with the generator and the spinor representation.
This is another way to see that omega has no symmetric part.
This is another, right. Because, right. Omega, right, has no symmetric part because that's what parameterizes the infinitesimal group. No symmetric part appropriately understood with the etas. Okay? This, and then we put a psi bar. What is psi bar? Psi bar is the usual object. Gamma, 0, psi dagger. Okay? There's not a Christoffel symbol in sight in this equation. There are spin connections. There are no Christoffel symbols because there are no space-time indices. The object that we're looking at is a space-time scalar, but is a spinor under this local Lorentz group. This is Dirac's Lagrangian in an arbitrary curve manifold. Beautiful, right? Okay, so we've answered Upmanyu's question. Okay, the last thing that we wanted to do with this formalism is we said to understand in what sense whether there is a clear sense in which general relativity was a gauge theory. Now you see we found one clear sense in which general relativity is a gauge theory. Because what's the essence of a gauge theory? The essence of a gauge theory is that you have these local transformations and a connection that helps you define derivatives that transform covariantly under these local transformations. We have the local transformations. What are they? Local transformations of SO3, 1. Local Lorentz transformation. We have a connection. What is it? The spin connection. But once you have a gauge theory, you like to compute gauge invariant quantities. Or at least gauge covariant quantities. We know how to compute the gauge covariant quantities for derivatives. But in a gauge theory, there's a very fundamental basic gauge covariant quantity. And that fundamental basic gauge covariant quantity is the field strength. Okay? Gauge invariant will trace f square, but at the moment just gauge covariant. So del mu omega nu minus del mu omega mu plus omega mu commutator omega nu. This quantity by the usual algebra of gauge theories is guaranteed to be gauge covariant. Okay? This quantity we're going to define as R mu nu. Let's call it tilde. Okay. R mu nu. Yeah, let's leave it. And of course,
This AB
it has matrix indices. So there's AB indices. I'll write them. This AB is equal to this object. Okay.
This can be proved. This is R mu nu.
This is my definition so far. Let me call this R tilde.
Okay, R mu nu.
Let me call it R tilde. Okay. Exercise. Show that that R tilde mu nu AB is equal to R mu nu alpha alpha beta E alpha. No, I want A. Alpha beta E alpha A E beta B. Wait. But this quantity is the usual curvature. This tells you that all the field strengths that we normally compute in a gauge theory, the normal information about field strength, is already contained in the curvatures of general relativity. So the curvatures of general relativity were secretly gauge theory curvatures. Okay? We didn't realize it because the gauge group in question had as many degrees of freedom as dimensions of spacetime, because we were doing SO3,1. So it was very easy to get confused between gauge indices and spacetime indices. But there is a way of thinking in which makes it very clear. These two are gauge indices, spacetime indices. These two are gauge indices. And when you look at this object, it is the usual field strength of a gauge theory, except appropriate to the gauge group SO3,1. Okay? And the way to go between any Vierbein index, any Vierbein quantity and any spacetime quantity is always dotting with this E alpha beta.
Then how we are getting the new information from the omegas?
We're getting no new information.
Oh,
Omegas, you see, omegas were completely determined in terms of ease, but the ease didn't matter because you change ease and you could change omegas in a known way. So it was really completely, in some sense, completely determined. The non-trivial information in omega is completely determined by the manifold. Okay? So for instance, if we compute a trace of R tilde square, it's like trace F square, like what we do for Maxwell theory. Okay?
The placement scalar, right?
That's exactly. So trace of this is what? This by definition is R mu nu AB R mu nu, that's just raised R mu nu, then BA. And then by inserting the appropriate e's, this is just R mu nu alpha beta R mu nu alpha beta. So any natural gauge theory quantity we want to compute, like the thing that would go into Maxwell's action, or the Yang-Mills action, is automatically can be automatically translated to some space-time quantity. Now this looks very somehow looks very different from, if you had not thought this way, you wouldn't have thought of this term as the analog of trace F square, or maybe not, I don't know. But it is when you think correctly. Okay? very useful in many ways. You see, because all of the technology that has been developed to try to understand gauge theory can be imported to the study of general relativity. And in fact, when a mathematician talks about the structures of a gauge theory, he likes to talk about these things which I only skimmingly understand. These bundles. And for mathematicians, the prime example of a bundle is the bundle of tangent space. And in fact, the spin connection is the curvature of that bundle. You know, so this language of gauge theory is very naturally incorporated into a study of geometry. Okay, very naturally incorporated in the study of geometry. You can define various invariants. For instance, just as a quick, I'll stop just a minute. Yeah. Most of you know that the quantity integral on a four manifold, f wedge f, is a nice, interesting topological invariant. Okay, that this is true independent of gauge group, and therefore it implies that integral r tilde wedge r tilde is a nice, interesting topological invariant. Okay, certainly in Euclidean space. In Minkowski space, there are possible subtleties. But certainly, if you were just going Euclidean, you were doing this is just an SO4 bundle. Okay, this in that Minkowski space, this will be quantized in the same way that we're familiar with in gauge theory. This will appear on the right-hand side of anomaly equations in the same way that it does in gauge theory. So many things and many structures in general relativity are very analogous to the structures, and in fact many of the derivations of interesting physical quantities go through when you think of general relativity as a gauge theory based on the gauge group SO3, 1. Just one last statement and then for instance, suppose you want to derive an anomaly. This is not for the course, but just for those who know. As you probably know, as most of you probably know, one quick way of deriving an anomaly is to try to understand how the measure of a path integral changes under the variable change that is associated with doing a symmetry transformation. Okay? Now, if you've got a fermion that is charged under the spin connection, but every fermion is charged under the spin connection, you might have contributions to anomalies associated with the spin connection. Okay? So just like you have d mu j mu is equal to f wedge f, you'll find that derived in Weinberg's book. If you just go through the derivation and keep in mind what r tilde is, you will also find an analogous formula like this.
But the current being?
It could be anything. It could be like the axial current. Okay? So a lot of the technology of gauge theory and the results of gauge theory can be incorporated into, you can incorporate gravitational effects very efficiently without doing any new work when you think of gravity as a gauge theory. This is a useful thing. It's also necessary to study propagation of fermions, and so it's very good to keep. It's sometimes essential, in other times good to keep in mind. Okay, I'll stop here.
So this R wedge R is that related to the Euler characteristic of the space-time?
Yes. Yes. That's right.